Hello everyone. In this lecture we are going to discuss about minimizing the states of a DFA. So we have already seen in our previous lectures how from a regular expression we can convert into a NFA, and from the NFA we can convert into a DFA. And this DFA we can implement this to form our lexical analyzer. So our lexical analyzer can be constructed directly from our DFA. But now, if our DFA that we have constructed consists of a large number of states, our lexical analyzer program will become much more slower as compared to a DFA with minimum number of states. So, given a DFA, if we can construct an equivalent DFA with lesser number of states, then the lexical analyzer that we can construct out of this will be more efficient in terms of both execution time as well as memory. So that is why we need to minimize the DFA to get a DFA with the minimum number of states. Now there are two different algorithms for minimizing the states. The first algorithm is the equivalence method, and the second is the table filling method. So we will start with the equivalence method. So in the equivalence method, let's say I have a DFA. Let's assume that I have a DFA which has got some number of states. Okay. Now from here I would like to reduce it and get another DFA which accepts the same set of strings, but now I want that the number of states is lesser. So here if I have 5 states, I would like to get a DFA with less than 5 states. So in this case example, you can see I have a 4. I want a DFA with 4 states. So to do that, there are two things that we can do. One is we can eliminate some states. Certain states we can eliminate, or we can combine some states. Okay, that is the way in which we can reduce the number of states, either by elimination or by combining. So for the case of eliminating the states, I just cannot eliminate any state. I have to eliminate only a certain type of state which does not contribute much to our DFA. And these type of states are called your unreachable states. Unreachable states. So how will you identify an unreachable state? Suppose I have a DFA like this. Okay, let me just have a DFA here. See, this is the final state. Okay, so I have something like this: 0, this is 1, this is 2, and say this is 3. Okay, so 0 on 1 goes to this, 1 goes to this. Okay, so 2 on 0 goes to this, and 2 on 1 goes to this. And let's say 1 on 0 goes to this, 1 on this goes to this. Okay, so here I have a DFA. Now if you look at the state 2 out here, you can see this state is unreachable. This state here is unreachable. Why? Because you cannot see any arrow that enters into this state. You can only see arrows which are, or transitions which are moving out of this state. So there is no way from the start state I can reach the state 2. So these type of states are your unreachable states. So if you want to eliminate states, then these unreachable states are the ones which you can eliminate, not the other ones. So the first step that we will do is we will have to eliminate, first we have to find out if there are unreachable states, and if there are unreachable states, then we have to eliminate these. Okay, and like I said, very easy to detect if it is unreachable. That means you will have, if you have a state, let's say something like this, say state Q, okay, if it is unreachable, you will only find arrows which moves out of this. You will not have any arrow which enters into this state, which transitions from some other state to this state. So these are unreachable states. So we are going to eliminate these. The other thing that we talked about is combining of states. Combining states. So how do we combine states? Now again, just like we cannot eliminate any state, just any state, we also cannot combine just any two states. So we can combine two states only if they are equivalent. Only if the two states are equivalent. So let us see how we can say that the states are equivalent. So let us come to this. So equivalent states. So I can say that two states P and Q are equivalent if I have, say, here delta is the transition, this is the transition, then P and Q are states, P and Q are states, okay, and W is an input string. W is an input string. So we can say that the two states P and Q are distinct, okay, that is non-equivalent if P is in the final state, P is in final state and Q is not in final state, okay, or vice versa. And delta of P on some input string W, okay, and delta of Q on again the same input string W are distinct, okay. So two cases, two states, if they are, in order that the states are not equivalent, then P must be if P is a final state, Q is not a final state, and vice versa. And the second condition is for any string W, input string W, delta of P and delta of Q on W must be distinct. So in that case, we can say that the two states are not equivalent. In fact, we can define something called K equivalence. K equivalence. So K equivalence means, again I have delta P W, okay. So depending upon the length of W, okay, if the length of W is less than or equal to K, so for any length of the input string which is less than or equal to K, then we can say that delta P W and delta QW, sorry, QW are equivalent if those two conditions are not satisfied. So that means if P is a final state, Q also must be a final state. And if P is not final, then Q also should not be final. Okay, and delta of P on W and delta of Q on W should be similar, should be from the same state. So, and if K is equal to 0, then we say the two states are 0 equivalent. Or if K is equal to 1, then we say it is 1 equivalent or 2 equivalent, and so on.